this lesson, you'll be pleased to hear this will be the last lesson in the integration for the pure maths, pure 2, chapter 11.12, integration is sum of limit. Now, this final part is a weird one. I think is something similar to like differentiation by first principle, where we go back to the roots of why integration is the area, finding out the area. However, it's nothing to do with integration by first differentiated by first principle, where it's, but we look into roots and we look into why area is the can be worked out using integration. So before we start, okay, let's do some drawing. Okay, so imagine, okay, so we've got in here we've got f of x, right? So we've got our x and y, and then here's a curve. Here's a curve. We have learned, okay, imagine I have to work out the area from A to B in here. I want to work out the area in between, okay? I want to work out the area in between. Now, what you've learned previously is to use, to estimate the area using trapezium rule, okay? So you can use trapezium rule, but imagine, okay, each trapezium rule in each strip, okay? So there are lots of strips in here. I'm not going to draw them all out, okay, etc. You get it. But imagine I'm going to zoom in, okay? I'm going to zoom in 1,000 times. Now imagine if I make a trapezium, now the strip is thin enough already, okay? It's thin enough, it's very thin, okay? It's very thin. Imagine I zoom in 100,000 times. Think of what shape would it look more like become. Now if I zoom in 1,000 times, it looked more like a rectangle. Now because you can imagine, okay, so that's this, so I'm going to zoom in 1,000 times. This is the strip of A. Okay, so that's line A, and this is the strip of, I don't know, that line in here. Okay, that orange line in here on top in here. Okay, then it becomes like a rectangle. Okay, so it becomes more like a rectangle. So it becomes like a rectangle. So becomes a rectangle. Now, in each rectangle, so in the rectangle in here, we call this value the y value because that's the y-axis. Because imagine that's the y value. So y1, y2, below trapezium rule, y1, y2, y3, yn. Or we can call it f of x because y equals f of x. And each of them, okay, if we in this large piece of trapezium, okay, we're going to break into many, many pieces of rectangle. Okay, it becomes a rectangle. So in each of them, we have equal strip of rectangles. We'll call this delta x. This symbol is like a delta. Okay, it's like a D. It is not like a D. It is a Greek letter D, a small letter D, delta. You have seen the capital D, which is actually like this, which stands for discriminant. Yes, discriminant back in pure 1. The discriminant could be used, the triangle means delta, so delta equals b squared minus 4ac. You've learned that actually in pure maths anyway, but that's not what we're learning today. The little symbol here, like a hanger, like an S with a hook or a hanger, is called delta. Okay, so delta x. This delta x is a very small value. Okay, just like delta x tends to 0. So delta x tends to 0. So that very small value tends to 0. So then if we want to work on the area of one strip, so the area of one strip that equals to length times width. We know with a rectangle, length times width. The length is delta x, okay, and the width is y, or we use f of x. So therefore, it becomes f of x delta x. That's area of one strip. Okay, so total area, between A and B equals to. So now remember, this is just in one strip. Okay, so this is just one strip of trapezium. In the one trapezium strip, we have many, many rectangles in there. So from A to B, we have that's the same as sum of area of all rectangle strips rectangular strips. So we call this, okay, so we use summation, sum, right? Summation, we start from x equals a to b of f of x delta x. Because the sum, we learn the sum, we can use summation. We learn this, and area of all strips is f of x delta x. So, but we also need to define f of x. Therefore, the final bit, okay, the final bit is that the area equals to limit delta x tends to be 0. Okay, very similar to differentiate by first principle, where you have to say limit delta x is tend to be 0. This delta x is a very, very small value of summation x equals a to b f of x delta x, which also now equals to the integral of a to b of f of x dx. So now this is a standalone chapter. You don't, if you're struggling to understand what's going on in here, I'll explain again. But if you're happy with it, you can move on to an example. So imagine, okay, we have to work with the area, okay, from A to B. We can use trapezium rule to sub-estimate. We can break them out into trapezium strips. In each trapezium strip, if we enlarge 1,000 times, zoom in 1,000 times, it becomes like a closed rectangle. And then in this large shape, we divide them into each strip of rectangles, because the trapezium itself has a really low incline line in here anyway. So it's, if this line on top becomes flat, that becomes rectangle. But imagine it's already so flat, it can nearly be a rectangle. Now, if we zoom in 1,000 times, then these little strips are clearly, it's going to be rectangle. It's going to be very, very close to rectangle. And this delta x is close to 0. So imagine the length is just 0.01 centimeter or 0.01 meter. Then it becomes like a rectangle, almost like a rectangle. So we can assume it's a rectangle. So the area of one strip is length times width. So it's delta x, the length is delta x, and the height is f of x. Now, why is not the length a? Because the a is just this line here is x coordinate. The width itself, the length itself is delta x, so times f of x. But the area from A to B has many strips. So we have to say, we have to use sum of all strips. To use sum, maths, we use sigma, summation, x equals A to B, and then the sum of all strips. So therefore, the area under the curve, area under the curve. Under curve can't spell, A, B. So area under the curve, let me write properly again. Under the curve, A, B equals to limit. There's this, delta x tends to be 0, summation x equals A to B, f of x delta x, which also could be written as what we now know as the integral of A to B, f of x dx. So the integral dx is actually this in Asian times. Okay. Right. Now, the understanding, if you understand it, brilliant. If you don't, it's not the end of the world, because you don't really need to know this. Now, however, if you do something, do math later on, then it's very, very useful to understand what's going on in here. But when it comes to the actual application to it, it's much simpler than you think. The diagram shows a sketch of the curve with equation y equals sine x. The area under the curve between x equals 1, x equals 2 can be thought of a series of thin strips of height y, okay, and with delta x and width delta x. Calculate limit delta x tends to 0. Now you see this delta x tends to 0 is not underneath, because when you type it out, they don't type it out nicely underneath. It's something to do with the latex programming. So and you can see x equals 1 is meant to be underneath, but it's not when you type it out. It's sometimes weird. Calculate this, okay? If you show it to someone, show it to a year 7, year 6 student, okay, show it to any younger year group, they'll be like, oh wow, you do crazy maths. It's like you meet a person, okay, they look crazy, they look so mean, they look horrible, they look unapproachable, and then when you go to them, it becomes and you find out they're actually like a big softie. So this is what it look like. So this limit, we don't care, or we can rewrite this if you like to. Summation x equals 1 to 2 sine x delta x. Now, if you look at what previous means, this is the left hand side, we can rewrite as the right hand side, which then equals to from 1 to 2 sine x dx. And that's it really. You just have to know how to rewrite it from here to here. And surely you should know by now how to integrate sine x from 1 to 2. This is probably the easiest. This will be in radians. So yeah, so there's the horrible mean person from the outside. And then once you get to know him or her, it becomes like a big softie, easy to manipulate. So pause the video, have a go, work it out for SF in radians. When you're ready for the answer, you can press play. So your answer, so if you integrate sine x, you get negative cos x, and you should have 1 to 2. And if you use degrees, yeah, you should be using radians, so you should have 0.9564 if I'm not mistaken. Yeah. Okay, so you do negative cos 2 minus bracket. Don't forget to put a bracket, minus cos 1. The minus makes a plus. So that's 0.9564. And yeah, and give yourself a round of applause because you have officially finished the whole integration chapter. But before I let you go, do the homework. So thank you for going through the journey of integration with me, and I hope you understand what's going on in here. Final bit. Remember RTSP when it comes to reverse chamber fraction, LNP. Okay, L stands for ln denominator, negative power, partial fractions. Okay, RTSP and formula booklet. Thank you very much.